Hello, everyone, and welcome to today's Bite-Size Talk. With us today is Tom from Policlinico Gemelli, and he's going to talk about a new nfcore pipeline called fastqrepair. And even though the name is probably also the program, I'm very interested to hear what he has to say. It's your stage.
Thank you for the introduction and welcome to everybody. Yes, the name is very meaningful. This is maybe the smallest pipeline that is stored in our database. And why I developed this pipeline? Because of important necessity that I had in the past. My FASTQ file got corrupted. And as you know, maybe better than me, this is a course when we have this kind of events because we lose tons of data. So this motivated me to develop this pipeline. So why this happens? And most of the time, a FASTQ file that is gzipped, so a compressed FASTQ file, because this is the point of the pipeline, is corrupted because of a problem during while transferring these files. Because sometimes when you transfer this file, we select an ASCII mode instead of a binary mode. This is most of the time this is the cause of the corruption. But sometimes, because this also happen, this happen because of connection failure or storage failures. In my personal case, my FASTQ file got corrupted because of a storage failure, because I had some parts of the disk that were broken. I didn't know, so my file were not readable. So this is the motivation. This was the motivation of the pipeline, and this is the whole pipeline. As you can see, is very small. It is made by 5 tools. There is the GZRT tool. I will introduce each of them in a moment. And so there is the central part is the FASTQ wiper tool. And we have a sub-tool of the BBMap collection of tools. And as usual, FastQC and MultiQC. I will introduce you each piece of this pipeline. The first one is the GZRT, that is also called GZ Recover. This is a very important program. This has been written by Aaron Wren. Is a C program that takes in inputs any kind of compressed file. But in our case, we use, of course, for FASTQ, for gzip FASTQ file. And you can specify by means of this argument -o the name of the recovered file. You have also other options, but in my opinion, one of the most important is -p, because you can pipe the output of this program to be used in a pipeline, as in our case, for example. So the reason of this tool is to take a broken gzipped file, in our case a FASTQ file, and it recover it and gives you a recovered FASTQ file. But the problem of the recovered file is that it is now readable, but inside you can find many unreadable, so not printable characters that are not compliant with the FASTQ file in general. So this is why we use wiper tools. I'm the author of wiper tools, and let me say that is a collection of tools, even if the most important tool inside is called FASTQ wiper. And the other tools are FASTQ scatter and gather. These are very simple tools because they can take a FASTQ file and they can split this FASTQ file in several. You can specify how many smaller FASTQ chunks. And of course, these chunks are have a number of lines that are proportional to 4, of course. And so FASTQ.gather takes the recovered FASTQ chunks and put them together. Report gather is also important because FASTQ wiper at the end of its cleaning job, it gives you a clean FASTQ file, but also a report. So report gather takes all the reports and put them together to give you just one general report. Okay, so if you just want to give a look at the arguments of FASTQ wiper, just two arguments are required, -I, so the FASTQ input, FASTQ output here. But you can also specify the frequency of the log messages on screen, or you can also specify to redirect the log text to a text file. You can also specify, this is important, the alphabet of the nucleotide sequence inside the FASTQ file. So the allowed character inside that string. So just to understand what I'm saying, and for who is not very familiar with the FASTQ file format, a FASTQ file format is a textual file that is made by multiple of these 4 lines. So it's not so difficult to understand. The first line is always a string starting with a hat. This is mandatory, this character, the first character, and after this character you have the name of the read, and depending on the kind of FASTQ file, so the technology that generated it, you can have, for example, the coordinates of this string into the plate that you made during your experiment. You can also have the length of these nucleotide strings, for example, but this is absolutely optional. What is mandatory is the at and the name of the read. So in the second line, you have the actual nucleotide sequence. So this is the alphabet that I told you before. So here we have ATCG, but if you want to allow also the presence of the N, for example, or all the other character, you need to specify the allowed character in the command line before. And then you have a third line. The only mandatory character is the plus. The plus is the character that separates the nucleotide string from the quality string. Everything after the plus is optional, usually is identical to line 1. And the fourth line is a one-to-one mapping. So you have one nucleotide and one character, and this character is an encoding of a thread value, so a quality value. So a number is encoded to a character by means of this very simple equation. So an ASCII character is equal to the thread value plus 33. Why 33? Because 33 in a ASCII map is the code of the first printable character. And if I'm not wrong, the last printable character has a value of 126, that is the tilde character. But at the best of my knowledge, we don't have quality value that our ASCII has 126, if I'm not wrong. Okay, so this is these are 4 lines of a FASTQ file. So your FASTQ file is made by millions of these lines, okay, inside. So this is the file format. So what that Wiper Tools does is a list of very simple commands. The first one is that it removes blank lines because they are not informative. and they could be introduced by the recovery stage of the GZRT tool. The second point is that it checks the header line, and so it looks for the occurrence of the @ character. If it identifies it, it says that this is the first line of a read. If there is a line that doesn't start with a @ it attempts to extract the portion starting at the last @ as a recovered header. If the line is not printable, because it can happen, it tries to recover a header from the printable string that is after the @ about the sequence line validation, it just rejects every not printable character, all not printable character, or all the characters that do not match the regex, a regex that is very simple, that just check that your alphabet is respected, is met with your nucleotide sequences. Otherwise, the other characters are considered not valid, invalid. So it just checked that we have a plus line. Okay, so reject not printable lines, or lines that do not start with a plus. Check the quality line, just rejecting not printable lines, or even in this case, the latest check is that the length of the sequence string, so the second line, if you remember, is this length must be equal to the length of the quality string, of course. And so, as I anticipated before, Wiper tools also logs after n reads. You can specify this and give you a report of the recovery statistics to screen or to file. Okay, so after that, Wiper Tools gives us all the chunks of the FASTQ, original FASTQ file clean. So you can gather all these FASTQ file, put them together, and optionally, you can use on this recovered and unified file the bbmap because this tool, what does it do? This tool, it repairs the reads that became disordered, because since you can also use paired end reads with our pipeline, you can lose one read in R1. You can have the mate and singleton, in this case, read in the R2, for example. So if we use this tool, you can give in inputs the R1 and R2, for example, that have been recovered by means of Wiper tools, and you obtain in out and out2 the repaired mates. But you also obtain in outs the singletons, that are the reads that have not that are singleton. And finally, because as I said, the pipeline is very, very simple, we run fastqc to just have a quality control of what we recovered, and multi-QC, of course. So this is the pipeline again. So in blue, you can understand now that we can process both paired end and single end read, in the single end and in orange. You can decide to scatter this FASTQ. And why we decided to do that? Because FASTQ Wiper is written in Python, so it's not so fast as we wanted. So we decided to do this. You can do this with, of course, with paired end reads and single end reads. So if you do a scatter, you need to do a gather. And just to say that GZRT is not optional, at least it has been represented, but GZRT can work, of course, only with the gzipped file. So if you provide, because you can do it, you can provide your FASTQ file that is not gzipped, because you don't want to recover by means of GZ but you want to clean it by means of FASTQ wiper, this step is automatically skipped. And on the contrary, BBmap repair can be decided to be skipped for paired end reads, because you can decide not to skip, to repair, to make this repairing, because this step can cause the losing of many reads that are not paired. And the rest is mandatory, but it's very, very simple. So in input, you can put your sample sheet. That is very simple. First column is the meta ID. Second column, mandatory, is a FASTQ file. The third column, optional, if you have a paired end, of course, the R2, and stop. This is very simple. And in output, you have the repaired reads with the name that you have specified on the meta ID, and a textual report, that is the report that is given by FASTQ wiper, and the HTML reports given by FastQC and MultiQC. So just want to share with you my first experience with Nextflow. I'm a computer science engineer, so I'm familiar with programming, but I have to say that my learning curve of the language was steep at the beginning, and in particular, I had some difficulties that still persist now, I have to confess, about channels manipulation. But on the other side, I have to say that the web is plenty of documentation examples, so anytime I could overcome my difficulties, so it's okay. But on the other side, plenty of enthusiasm, especially because portability of the pipeline, and it's also very simple to port my pipeline on the HPC architecture. So very, very, very happy with this. And the last part, also a great community. You don't feel alone. I didn't feel alone in this short experience, and plenty of great guys. So I approached the end. So thank you very much. And if you have any question, and I'm able to reply, very happy to do that.
Thank you very much. So with this, I would like to open for questions from the audience. If anyone has any questions, please unmute yourself and ask them directly. I actually have a question myself.
Yeah.
So
Thanks.
the first one, actually I have two. The first one would be FASTQ wiper. Can you actually run that without an output file, or like just having the report as an output file, like as a kind of a QC that will give you a report in the end?
Yeah. The report is very simple. It's just a textual file where we have the it's a QC report where you have the total number of processed lines, the total number of recovered lines, and all the problems that have been met during the processing, and which one could be fixed, because sometimes we can fix, for example, the header. There sometimes happens that when you use the GZRT tool, you have a header line, but that doesn't start with the head character, because this happens because something mess up around. No, so the program goes to the likely header line, look for the head character, so discard everything before, and consider the header what is after. This could be also garbage, but the consistency of the process is that after this line, it look for the nucleotide line. So if after that you don't match the alphabet of your nucleotide sequence, it skips completely the reads and start again looking for the other line. Okay, so you can see everything in the reports.
Right, but it means also that you cannot have a report that actually has everything included without manipulating, let's say, the files or writing out the correct file.
No, sorry, I wasn't clear. Yeah, we output both the report and the clean file. Yes, of
Yes,
course.
but let's say you only want the report. You don't
Yeah,
actually want a
no,
cleaned file afterwards. You just want a report saying these are the
yeah,
data issues that you have.
yeah, no.
Is that possible?
Yeah, it's possible. Yeah, could be. Okay, it's possible to do. Yeah, we need to do this. Yeah,
Okay. And the second question I had was how long
yeah.
does it take to run this? Like, is it something that is very extensive or is it run in 5 minutes, depending on file
No,
size?
no, no, it's expensive. Yeah,
Yeah.
expensive and intensive also, of course. Yeah, because the most intensive calculation is wiper tools. So what is in the middle here? Because it is written in Python, I say again, because it does something that maybe is not I should improve in the future, because I used at the beginning a regex to identify the correct nucleotide sequence, but maybe it's not necessary to do this, because you can just look for your alphabet into your string. That is much faster. And so processing a textual file in Python is not so efficient. So that's why if you have a processor, you need to scatter your FASTQ file. So to process a genome, a whole genome, you could take a couple of hours. Yeah,
Okay.
yeah. It's
Thank
not so fast. It's not a fast process. Yeah,
So do it if you have to, not if
yeah, yeah,
just
yeah.
as a regular
Exactly.
thing. Okay, cool. Okay, are there any more questions from the audience? Otherwise, I would like to thank you very much. I really like your pipeline. I like your presentation.
Thank you very much.
Very cute. And thank you to the audience, and I hope to see you for our next bite size as well. Have a good day.
Yeah.
Bye.
Bye bye. Bye bye. Ciao.